Good morning, students. So, today's class we are going to study about the basic bioelectric signals, electroneurogram. So, electroneurogram means study of electrical activity of the nerves. So, that we call it as electroneurogram. So, here to measure the electroneurogram, we used to conduct the nerve conduction velocity and study. We will be applying the stimulus to the nerve, and then we find the response of how the nerve is conducting. And if you see, to record this electroneurogram, we'll be using a concentric needle electrodes that will be pierced into the skin, into the nerve. It will be the tip of the needle will be placed in the nerves, and then to record the electroneurogram. And sometimes we can use the surface electrodes also. It is the silver chloride electrodes to record this ENG. So either needle electrodes or surface electrodes will be used to record this electroneurogram. Actually, why do we go for measure this electroneurogram is to check whether the nerve is conducting properly or not. For normal people, okay, but in the case of paralysis patient, so the nerves will be conducting at a very late only. So that's why people used to give a small kind of a current shock stimulus in the small current in the terms of milliamps range. They will be applying as a stimulus to the patient and then check whether the patient can able to respond to the stimulus. By that way, we find out the nerve conduction for the paralysis subject. So, in your uh, biomedical instrumentation subject, so most of you have conducted this nerve conduction velocity experiment. So, in that, you can able to see that a ring kind of electrodes, it will be placed on the finger and another electrodes will be placed above the elbow. So now a small amount of current, it will be passed to the ring electrodes, and one end of the ring electrode, it is connected to the amplifier, ENG amplifier. So now a small amount of milliamps, in the terms of milliamps range, current is passed to this ring electrode. So that time the person will feel some kind of a shock. So we used to calculate the nerve conduction velocity by the time which is taken for applying the stimulus and getting the response of the nerve multiplied by the distance between these regions, that is the ring electrode and the electrode which is placed above the elbow, because through that path only the nerve conduction takes place. When you apply the current to the ring electrode in the finger, so the shock we can able to feel at that particular regions above the elbow. So through this the nerve conduction takes place. So the nerve conduction velocity is calculated by the formula distance into time. So time here is the time taken for giving the stimulus and getting the response. That period we call it as a latency period. So that time we can calculate the time, and the time will be multiplied by the distance. So this will give you the nerve conduction velocity. Through this nerve conduction velocity, we can able to identify whether the nerve is conducting properly or not, or it gets delayed. So here um, the amplitude of the nerves, it is given by in terms of 100 volt amplitude, and the time duration, it is defined here as 100 to 300 microseconds duration. And while you're recording the ENG signal, so there will be some difference in the latencies. Latency is nothing but the time which is taken for giving the stimulus and getting the response. So that period we call it as a latency period. So a difference in latency periods of the ENG signal, it is recorded over the associated muscles. So this will give you the conduction time. And knowing the separation distance between the stimulus sites, it is possible to determine the nerve conduction velocity. So generally ENG signal have the amplitude of order of in terms of very less in range is 10 microvolts, and sometimes while you're recording the ENG signal, it may susceptible to some power line interference and instrumentation noise, because you're connecting the ENG amplifier to a power socket in which power supply is given to the EMG amplifier. So through that power socket, there is a chance for power line interference, 60 hertz interference get overlapped with the ENG signal. So that is the kind of an artifact which is associated with the ENG signal while you're acquiring. So that we have to do some signal processing operation to remove those artifacts. Now you can able to see that this figure represents the ENG signal which is recorded over the wrist region, elbow, below the elbow region, above the elbow regions. Three different regions it is given. So they have given the stimulus and record the response. And if you observe the waveform, so it is like more or like an action potential waveform. So let us see the first waveform. It is in the wrist regions. They have recorded this ENG signal. So initially there is a the stimulus is not given. Once the stimulus it is given, what will happen? The potential starts rising. That means the nerve is starting conducting. When the current is given, the potential flows here. So when it is recorded, you can able to see an increase and a decrease in potential here. So which is observed as a wrist in the wrist region. Then the signal ENG signal which is recorded over the below the elbow region and above the elbow region. So if you observe all these three waveforms, you can able to find out the difference. So the difference is here is the latency period. So here you can able to see at different regions you have different latency period. So you see you can able to observe that in the wrist region the latency period is less, whereas in the elbow the latency period is more, and that is below elbow, and above elbow again the latency period is high. So there is an increase in latency period with respect to the stimulus point. So that we have observed in this graph. And if you see the nerve conduction velocity, so it is from below the elbow to the wrist, it is 64.9 meter per second. And here they will be placing the surface electrodes over this wrist or below elbow or above elbow to record this ENG signal. So the amplifier is amplified with a gain of 2000, and the frequency range which is used is 10 to 10,000 hertz. And if you see the typical nerve conduction velocity values in the case of nerve fibers, the range is 45 to 70 meter per second. And if you see the heart muscles, so definitely there the nerve conduction velocity is less only. It is zero point 0.2 to zero point 0.4 meter per second. And in the case of the conduction, when you nerve conduction takes place between the atria and the ventricles, so it is very low in nature, so 0.03 to 0.05 meter per second. So when the patient is having for paralysis patient and all, the nerve conduction velocity will be very less only, because the nerves takes longer time to response in the case of paralysis subjects. So when there is a decrease in the nerve conduction velocity, when the person is having any neural disease, any neurological disorders, psychological disorders or mental disorders, for any kind of neural disease, there is a decrease in the nerve conduction velocity. Thank you.